So guys, welcome to the third IAP that we have done. Last year was about extending large language models with things like perception and reasoning, language. This year is something pretty different. So if you're not familiar with Gridspace, we are a speech and language technology company focused on long-form conversational speech. And what we work on is mostly audio. So this IAP series, which is going to be 12 lectures over the course of January, is going to be about sound and voice synthesis. And so we're going to jump into lecture one, which is engineering a song from scratch. This is like not that technical of a lecture compared to I think a lot of the rest of them. So hopefully it'll be kind of a fun intro. But we're going to start with a sine wave. Cool. All right. So we're talking about building a song from scratch. This is a sine wave. This is going to be our first target here. So we are going to switch over to the terminal again. Nico, tell me what a sine wave is.
It's a function with the value of the trigonometric function sine of x.
Oh yeah, so Nico's saying it's a value or a function with the value of the trigonometric function sine of x. So the geometric sine function from geometry.
Yeah.
There's also an analytic sine function. Sine function. Well, let's talk about the exponential for a second. The exponential in analysis can be defined as a power series, right? So you can think of it as 1 plus x squared over 2 plus, or sorry, we have x plus x squared over 2, etc. And you can literally take that as a definition of the exponential, and you can actually define, a function for sine that is e of basically ix minus e of minus ix, all of that over 2. And you can then later prove that that analytic sine function is the same as the exponential function. Why am I talking about this? I'm talking about this because I don't really care about the geometric interpretation of the sine function. The reason sine functions or waves shaped like a sine wave show up so much in sound is because in differential equations, the solution to any simple oscillating system, a simple harmonic oscillator, is a function that has to have the properties of a sine or cosine wave. So we're trying to build that because that's what sound is built from. So we're going to define sine x here. And can someone tell me analytically, based on kind of what I was just showing, how could you build a sine wave? Nico?
You could take the real part of a phasor.
You could take the real part of a phasor. Good answer. The answer is we could build a series, right? We could build a Taylor series, right? To first order, sine is just x, right? So we're going to start with that. So we'll see how that does. All right, so we need a couple things if we're going to make sound. We're going to define all these things in more detail in later lectures, but we need the sample rate. So 44/100, that's the most common sample rate in digital audio because it's about double the limit of hearing, which is about 20,000 hertz. And so this guarantees that any sound that you can hear can be reproduced by the computer. We're also going to pick a duration of, we'll say 2 seconds, and we're also going to pick a frequency for our first wave here, and we'll do an A440. All right, so now we're actually going to make our sine wave. All right, it's going to take a duration, sample rate, and a frequency. All right, cool. So we're going to build that out with NumPy here as an array. All right. We're going to build out our wave for that frequency. And we're just going to say sine from above of angles and return our wave. So this should allow us to build a sine wave, right? So last thing we need to do is actually play it to my speaker here. And so we'll do play for our sample rate, and then we'll wait. And that should be it. Does anyone have a prediction what's going to happen given my sine of x of x? Nico. It's gonna sound like shit.
Not gonna sound like anything.
Wave is not defined. Yeah, that's a good answer. All right, so we're gonna do something like this and just say that x2 times x. We're gonna get x, the fifth power of x, do x2 times x3, and we're gonna do x7 equals x2 times x5. All right, and so we're gonna make a better approximation from these. So we're gonna add a term, which is x3 divided by 3 factorial, plus the next term is x5 divided by 5 factorial. And does anyone know 7 factorial off the top of their head? MIT students? All right, cool. Any predictions? How's it gonna sound now?
Like an A440.
Sounds pretty similar to me. All right, anyone guess? You kind of already answered it earlier, Nico, but what's the problem now? Any guesses? Will?
I thought it sounded like it was supposed to sound.
Yeah. It's supposed to sound like beautiful music, guys. We're trying to make an engineering a song from scratch. So yeah, it's a cyclic function, and so you can't, there's no Taylor series that's going to converge to infinity. And so typically what we're going to do is we're going to choose a very small region, and we're going to take advantage of symmetry to restrict it to that region where we have a good approximation, which is near 0. So we're just going to take it. We could actually do better than this. Oh, we have a question? Can you turn on the mic? Turn on the mic?
Cole Frank's answered making periodic.
Oh, so Cole Frank's got it right, but unfortunately, but I think Nick Cole, who used to teach math at MIT. So yeah, is he? Can you ask Cole if he's feeling better from his flu?
I think you can ask him.
I can only do this. Wait, hold on. Oh, all right. All right, we have an A440. Cool, and this is without using a library sine function, which people know is something I like to do. All right, cool. So we're going to keep improving this. By the way, so frequencies are perceived logarithmically, right? So if I have this frequency, sounds like the same note. Same with I double it. The reason this sounds like the same note is because the ear, the cochlea, is an Archimedean spiral. And so in general, doubling or having the frequency is going to excite a lot of the same cilia in the basilar membrane in the cochlea. And so it's going to sound like a similar note, similar to those other harmonics. And so similarly, intensity is perceived logarithmically as well. Like I can multiply this by 0.1, so make it like 10 times softer. But that's going to sound to us like it's more like 3 times softer, or 3 decibels. And similarly, if I make it 10 times louder, this will probably clip. Sound really bad, but let's see. That'll be fine. So I don't know if that sounds 10 times louder. So both the frequency and the intensity are perceived logarithmically. What else do I have here? Oh, right. So, what if we wanted to make a chord? So we could say wave plus equals sine wave, and we could say same duration, same sample rate, and we could do 554.37. Does anyone know what note this is? Or want to guess? It's the C sharp above the A, so this is the major third. We could add another one here. There's a major triad. All right, cool. So that seems to work pretty well. What else can we do? Can anyone tell me something that makes it not sound like a real instrument? Maybe someone remote? Anyone on the chat? Anything we could do to improve this? It's like a 20-second delay. It's all right. In the meantime, we'll just play.
I'll tell you.
You'll tell me? All right, cool. So, Nico, what can we do to improve this?
Harmonics.
That's a good thing we could do to harmonic. Is we could add harmonics. For those that aren't familiar, in general, really, and we'll talk about this way more on Thursday when we talk about additive synthesis, but we'll go back to the presentation.
The chat has answered. Ruji's answered add harmonics.
Could you do that in the microphone? I couldn't hear it. And yeah. So.
Ruji answered add harmonics.
Add harmonics, yeah, exactly. So here we saw this already. We looked up these notes. All right, cool. So here's a couple instruments here. So notice like the flute, the first overtone, or the first harmonic, which is basically a doubling of the frequency, is maybe about 60% of the tonic, or the primary harmonic. And then the next harmonic is much smaller, and then you have another one that's about the same size, and then a really small harmonic. Oboe has a much larger array of harmonics, which will make it sound louder and higher pitch and more shrill, kind of like a square or triangle wave. And you see the violin has slightly different harmonics as well. This is called the timbre of the instrument. So one thing we could do is just start adding some of these, as you guys suggested. So we're going to add some harmonics here. Oop. Actually, real quick, let's go ahead and put this in a while loop. So it's looping. All right. So let's start with the harmonic series for a this is for a flute. This is just reading off that graph I saw earlier. And then we'll just say for some multiplier and the ratio of the intensities in harmonic series. So what we're going to do is we're just going to take the wave, we're going to add in its relative intensity times a new sine wave, and this is going to take in same duration, same sample rate, and then it's going to take the frequency times this multiplier, the harmonic multiplier, right? And notice that these are just the fundamental frequency times 1, 2, 3, 4, 5. If you study like partial differential equations or Fourier analysis, you'll learn about why those are the multipliers for the harmonics. It'll probably be covered in one of the later lectures, but I'm not going to cover it. I'm just trying to make music for you guys. Just like a flute. All right, let's try an oboe. See if that sounds. Actually does kind of sound like an oboe, I'm not gonna lie.
It's like a cross between an oboe and an Amber Alert.
All right, what's something else that we can do to improve this, to make it sound more like a real instrument? Nico?
Reverberation.
Reverberation, like a tremolo kind of? Or like reverb?
Like, yeah. Reverb.
All right, we're gonna do that later today, but I'm gonna add tremolo and pretend that's what you asked for. So this is, here we're just going to basically add a sine wave on top of its intensity. And this, one is here, so we retain the core here. So typically when someone plays like a wind instrument, they normally add a little bit of tremolo, a little bit of a waver and an amplitude. Oop. All right. Cool. That sounds perfect. All right. What's another thing we could do? Like, let's say we were playing a chime. What would it sound like if you played like a chime, like hit a percussion instrument?
There'd be some kind of decay over time.
Yeah, there'd be like an envelope, a decay. So what we can just do here is just multiply it by an exponential. And I have a nice picture of this that we can look at together in a minute. All right, so we'll add like a little envelope on it. All right, so we did making chords, harmonics, envelopes. All right, so we're trying to make like it's from bytes to beats. What would normally be the first thing you would add into like an electronic synth song to make the beat? Will? Or Cooper?
Let's start with bass.
Start with bass. So we put 4 on the floor. Nico, what does 4 on the floor mean?
That means you hit the bass drum 4 times in a measure.
All right, cool. So we're gonna try
Tonic ideal for drumming, really.
the tonic ideal. All right, so we're gonna drop this frequency, try to maybe to get it to sound a little bit more like a bass drum here. Maybe let's speed it up a bit. I wonder if we want these harmonics or not. Probably not, because it's not a oboe. Oop. Great. Okay, after a bass beat, what would you normally add?
Snare?
Like a snare. So, by the way, here's what a typical envelope is. A simplified envelope is often modeled with an attack and a decay, which we didn't do. We really just did a decaying release, or I guess it's this decay. We just had an exponential decay. This is like a spectrogram. So this is, frequency versus time for different types of instruments. So we're going to be talking about all of these things in the class. So a vocal, which we'll be talking about for 2 weeks, has all of these layers called formants. And we're also going to be talking about formant synthesis in a week and a half. Drums, like a snare drum, have these really broad, even spectrum. So this is like white noise, basically. That's why a hi-hat sounds like ch. If you were to sustain it, it sounds like white noise. A bass, like we just made, is just a low single frequency with maybe a couple harmonics. So that's what we just did, right? So we're check. Guitar, if we wanted to do that, we would also probably want an exponential decay, and we would look up guitar harmonics, or we would do it some other way. We're going to learn like 50 ways to do this in the class. But a snare drum, we need this kind of white noise. So there's a lot of ways to make white noise. We're going to do it a pretty easy way, but we're going to do it more and more fancy ways later. and we're going to have the special guest on Friday, noise engineering, so maybe they'll be able to teach us. But today, if we wanted to do it, I'm just going to say instead, we're going to do wave equals random.random. Or sorry, no, I want this for my sine wave up here. And I think we need to import random now. So this would be white noise. If we wanted to shape that noise, we would probably use filters like a Butterworth filter. And by putting it through high and low pass filters, which we're going to do later today, you can shape those sounds so that it sounds like different instruments. When we talk about subtractive synthesis, we're going to be talking about, I think, Nico, you're teaching subtractive synthesis. So he'll teach that, and I will not show up to his lecture and support him.
I'm going to ask you a question every slide.
All right. So we know how to do a bass drum. We know how to do like an instrument with harmonics. We know how to do maybe kind of a hi-hat, like a low grades a hi-hat. Now we need to put this all into like a song. So we need like a sequencer. There's a couple ways we can do that. We're gonna create this like little mini version of MIDI. So I've written this in advance here. So we're gonna go. So I have written up my own little, here's my song here. Oop. So here's my song. This is a little CSV here and my own like miniature version of MIDI. So up here at the top, I've put like my tempo is 120 beats per minute. And I have 4 instruments. So I have instrument 0, 1, 2, and 3. So I have 4 channels. For each one, I have the instrument number, and then I have its frequency, and then the velocity or the intensity, and then whether it's on or not, right? So here's my bass drum, right? So I'm going to assign this to be the bass drum like we just made it. So you can see it's every beat, and then here's my hi-hat over here. And the concept of frequency is like kind of hard to define when it's white noise, but you're shaping the noise in theory. In reality, we're doing a really simple noise, but we're going to put everything through a filter in a bit. So this is on the offbeats. And then actually I think this might be another drum, and then we have the hi-hats here. And then we finally have a melody here. And we have a couple songs that we made. I've gone ahead and in advance put together put all this stuff that we just did into, where is it? Simple sequencer here. So this is like 120 lines of Python now. We have a parser for our little sequencer. We have a sine wave generator and a noise generator. In this case, we're just using NumPy now, and I'm no longer building Sine from scratch. I'm just using the NumPy library for Sine. But if you look up how it uses it, does it imports glibc, and glibc does it exactly like I just did it, but in C. So then we have this kind of channel manager. And actually what I'm going to do real quick is we're going to separate the channels for a second. And we're going to say if channel not in 1, continue. And we're just going to isolate these channels one at a time. And so then I also have a resonant filter. And we're going to talk about this a little bit today and then a lot when we talk about subtractive synthesis, or rather when Nico talks about it. Then my sequencer itself, which is just stepping through the 16 steps in my 16-step sequencer, and this mixing everything together, trying to keep it from clipping, and it's also putting in the filter. And so I've commented out the filter. We're going to turn that on in a second, but let's go ahead and listen to it. All right, so this is just our bass drum here. That's the only channel I turned on. So let's go ahead and add, I think there's another bass drum I put in here. It's not that low. I guess that is that little hi-hat. Then we have a third percussion instrument. Oh, you know what? I know what the problem is. There we are. go back. So channel 0 is, there we are. So now this should bring in our hi-hat. And then finally our beautiful melody. So now the biggest problem is these are all just raw sine waves, raw white noise. If we want to start to shape this, start to make it sound more musical, normally per instrument, we'd like to start adding filters on top of it. Now there's different types of filters. So if we look real quick. By the way, if you can kind of hear the bass drum, very low single frequency, the hi-hats, full spectrum of frequencies, and then our instrument is, you know, sine waves or sine waves with harmonics. So this is an example of a simple resonant filter, or specifically it's the resonant filter I built. So this is using something called the Chamberlain step variable, which we're not going to talk about today. But the main idea is that it's a resonant filter. It's resonant because it has feedback, and the feedback can cause resonance. And so there's two parameters. There's a cutoff and then the resonance frequency. And those two parameters will affect how much of a low-pass filter it is, and then also how much resonance there is, or how much feedback there is. And just from a very simple filter like this, you can get a pretty wide range of sounds that actually start to sound pretty like legitimately musical. So we're going to go ahead and turn that filter back on. If I can find it. And we can set different values interactively here. And we're done. So we made a song from scratch. And that is our introduction to building a song from scratch. Thank you guys. Introductions.
Welcome to the 2025 Gridspace IAP. My name is Grace, and we're so glad to have you here. In this lecture series, you'll learn how to generate sound using methods ranging from signal processing to generative neural methods. You'll even learn how we make a voice like mine.
So this is what this course is about. We're going to be talking about the physics of sound. By the way, I'm Anthony. I'm co-founder of Gridspace. I'm filling in for Natalie, who is out because she's not using the Gregorian calendar today. But she will be in for most of the lecture series, but I'm sure a lot of you have already talked to her over email. We're going to talk about the physics of sound. We already did a little bit today. We're going to talk about signals and DSP and signal processing, a little bit of even analog signal processing. We're going to be talking about different methods for sound and music synthesis, which today was kind of a taste of. We're going to talk about this history of speech synthesis, and we actually have speakers that were pioneers in the speech synthesis field. We're going to be talking about neural generative models for sound. All from spectrogram generation, vocoders, autoregressive methods, non-autoregressive methods. And we have many special guests. So we have the inventor of FM synthesis. We have noise engineering, the synth manufacturer. We're going to be here on Thursday. We're going to have performers. We have the inventor of Guitar Hero, the inventor of the TI Speak and Spell speech synthesis chip, and a bunch of other really cool people. We have a great YouTuber who does from first principles, from Navier-Stokes equation, physical modeling of instruments, and we're going to be covering a lot of really cool stuff. Just like every year when we do this IAP course, these are kind of the goals. So one, it's like a very engineering-focused deep dive. We're going to be celebrating 100 years of sound technology, from mechanical and analog systems up through deep learning. There's going to be something for everyone, so if you have limited knowledge, I think there's always going to be something to learn. Should be fun for everyone, especially because we're going to be doing a lot of stuff with like sound and music and speech. We will have challenge questions, and we're going to, if you come to all 12 lectures, you're going to get a shirt. So I know, by the way, Nick, can you come up here actually with one of your cards? Do you have one of the cards? Oh yeah, great, perfect. So I don't know if am I on camera, Kevin? Yeah. Yeah, so this is one of the attendance, and we're gonna give do a little stamp here and put your name on it. And if you come to all the lectures, you'll get a very cool shirt. This includes Gridspacers. And so if you attend each of the 12 lectures, we'll be rewarded with an exclusive Building Sound t-shirt. Leftover shirts will be burned. So there you go. Kevin made these. Are awesome, by the way. You'll get the card as well with your shirt. So thank you everyone who signed up. So this is kind of how it's going to work. Prerequisites, it's not a super complicated course. A lot of people doing IAP at MIT are freshmen and sophomore. So we want excitement about machine learning, excitement about sound, some programming knowledge. Obviously today I spent most of the time in a terminal, but there's probably going to be a mix of programming and math and music. Some familiarity with mathematical language of machine learning, calculus, linear algebra, and a little bit of familiarity with how sound sounds to your ear when it makes sound is good, because we're going to be talking about sound for the whole time. Speaking of which, here's the schedule, and Natalie will be going through this more with y'all on Wednesday. Today was this lecture, Engineering a Song from Scratch. This is just meant to kind of give you guys a taste of what we're going to be doing. Then we're going to be talking about acoustics and signals. And then we're going to be talking about additive synthesis and modular synths. And we're going to have a special guest, which is noise engineering. Then next week, we're going to be talking about shaping waves using subtractive synthesis. So if you like that, like resonant filter, you'll probably love that. And then we're going to be talking about other more exotic forms of synthesis, like wavetable, granular, and formants. We'll also be talking about samplers and sampling. And then the 17th will be about FM synthesis. And we actually have John Chowning, the inventor of FM synthesis. So this was used in like the Yamaha Odyssey and the Super Nintendo and a lot of 80s music, Michael Jackson music. Then on the 20th, we're going to be talking about physical modeling, and we have a great guest who's an expert in physical modeling. Then we're going to be talking about, we're going to be switching to TTS. So we're going to start with early forms of TTS, parametric and concatenative speech synthesis. Then we're going to be talking about the history of speech synthesis. There's a really long and storied history. We have several people who are pioneers in the field who are going to talk about that with us. Then we're going to be talking about early neural TTS, so from the last 10 years, starting with like seek-to-seek models and WaveNet. So like with like DeepMind's early model that took 10 minutes to make like a sample. We're going to be moving on to faster methods like tachytron, spectrogram generation, and vocoders for inverting spectrograms. And then finally, we're going to finish out with the most modern models, so variational models, few-shot replication, VITs. And then we will be done with January and done with the course. So the course lead is Natalie Bechet. She is not me or here, but she will be here, and she will be on Wednesday. If you have any needs from the course or course support, you can email IAP at gridspace.com. Some of you already have, and I appreciate that. Invite your friends. Anyone's welcome. You don't have to be an MIT student, but if you are, it's on the official listings for IAP sites or IAP classes. We are going to be releasing the videos so you can catch up if you're gone on YouTube, but you have to attend to get your little thing stamped. And meeting invites and YouTube streams. So thank you, by the way, guys, for moving over to the YouTube. In general, you're welcome on either of them. We'll be monitoring the chat on either of them. We'll hopefully, get the issues better by the 12th lecture. We'll be posting the recordings, attendance cards we talked about. You're welcome to come in person. So last year we had a good number of people. Some start coming in person. I think we have some people from USC and from AILA that were interested in coming later this month. And we will have, for instance, Thursday, we're, going to be demonstrating hardware in here. That'll be a really fun one to attend in person. All right, well, thank you guys very much. We're really excited about the series, and I know Natalie's very excited about it. And I think we're going to open up for questions.
Will the code be shared as well?
Will the code be shared as well? Yeah, sure. We're happy to share all the code from today and all the codes from the later lectures. And by the way, in the past IAPs, we've done projects. We don't have formal projects this time, but if anyone wants to do something, we will provide mentorship and guidance on it. So reach out to us if you want to do a project as part of this. Or hack on any of the stuff that we did on any of the earlier lectures.
Let's have a song contest like Eurovision or maybe award an IAP Grammy.
Oh yeah, IAP Grammy. Yeah, we can do a song. So the question is, can we do a song contest like Eurovision? And I think we'll do a song contest, but we're not going to do anything like Eurovision. Yeah, I don't know. Maybe Daft Punk will be a special guest. I don't know. Or Kraftwerk. Could be. Who knows? Trent Reznor. Any other questions in yet? No. So the question is whether my sequencer identifies attacks and sustains. And no, it's just literally just channel on for that beat.
So did you lose your decay?
Yeah, I didn't bring the decay in there. Yeah. But just if it wasn't clear what I was doing, I started from scratch, kind of showed you different effects that you can do, and then I switched to a very simple 120 line sequencer I wrote that basically just has a sine wave and noise generator and a reverberant filter. I didn't, but we can do it now.
Do it.
All right. So the question is, have we tried detuning the harmonics? But we have the power to do that, I think. So let's see here. And what that means, if you're not familiar, not that I explained anything else that I did, is you can take a harmonic and make it slightly different than the formant, and that can cause really cool effects. So we're gonna go back to our live code that we built together. And what we're going to do is add a harmonic that is slightly different than the frequency. So let's make it something like maybe we'll do an A440 again. And we're going to, let's get rid of this tremolo. Well, we'll keep the tremolo, why not? And we'll add a wave. And we'll just like add to the frequency 1 hertz. Had I done something that messed up? Oh, with a random. Left this in a state of shambles. Yeah, let's try tuning it a little more, or a little less. What do you think?
Maybe a little. You do it without again?
Okay.
With no detuning?
And you know what? Let me take away the decay. Or do you like the decay?
Yeah, take it out.
So there's a little bit of tremolo in there.
Right.
Yeah.
Maybe detune it more then.
That's it. That's cool. Do we have any other questions, Nick, while we were doing that? Sorry, he was with the decay, by the way. It's pretty cool. Thank you guys for joining, and we will be back at the same time on Wednesday to talk about acoustics, audio, sound, signals, and all that sort of stuff. So thank you guys very much.